Hello, welcome back to Learn Physics. In today's topic, it's a revision topic for gravitation chapter. So in the last videos and all, we did the revision for our work, energy, power chapter and then system of particles and rotational motion. Today we are continuing with our gravitation chapter. So as I said in the previous videos, all the detailed explanation of all the topics I have given in the playlist, or that will be there in the description box also. If you have any doubt in this explanation, please check into that videos. Okay, so now I am starting a quick revision for your exam point of view. I am telling this. So all the detailed explanation of derivations and all will be there in the respective videos which is given in the description box. Okay. So here in gravitation, first you are studying about Kepler's laws of gravitation. Kepler's laws. 3 laws are there. First one, law of orbits. What is law of orbit? Every planet revolves around the sun in an elliptical orbit. So this is the orbit, and if this is the planet, this is sun. So if all the planets are revolving around the sun in an elliptical path with the sun at one of its foci. That means for an ellipse, we know it has 2 foci, F1 and F2. So planet is here in the elliptical orbit, so sun will be at one of its foci. Okay, so that is the law of orbit. Every planet revolves around the sun in an elliptical orbit with the sun at one of its foci. That is law of orbits. Next is law of areas. Law of areas means, see, this is an ellipse. So this is major axis and this is minor axis. And this is the position of sun and this is the position of planet. The line joining sun to the planet sweeps out equal areas in equal interval of time. So the line joining sun to the planet, suppose if it comes here, delta t. In the same interval of time, the area which is covered will be same. The area covered will be same in the same interval of time. So while we are telling that as a law, the line joining sun to the planet sweeps out equal areas in equal interval of time. Next is law of periods. So what is this law of periods? See, the square of the time period of revolution is directly proportional to the cube of semi-major axis. Okay, so it is the cube of semi-major axis. Square of the time period is directly proportional to the cube of semi-major axis. Semi-major axis means this is the major axis and this is the minor axis. Okay, so semi-major axis means half of this major axis is semi-major axis. So law of period states that square of the time period is directly proportional to the cube of semi-major axis. And here we can say this law of areas can be understood in terms of the conservation of angular momentum. Okay, conservation of angular momentum. Okay, law of areas can be expressed in terms of this conservation of angular momentum. See, if I am considering this OAB, this small triangle while I am considering, what will be the area of the triangle for an interval of time delta t? Area will be equal to half into base into height. Isn't it? So half into what is base? AB into height is this distance. What is that distance? OA or OB we can write down. Okay, so half into here AB and OA. What is this AB? If V is the velocity, AB distance covered will be equal to V into delta T. Velocity into time is distance. OA, that will be the radius vector. Okay, so this one I can write it as, if I am multiplying one m in the numerator and one m in the denominator, mv divided by m into r delta t. Okay, what is this mv? mv is p. So I am writing this as delta A by delta T will be equal to, delta T I am taking to the other side. So half into P into R by M. We know it as L, P cross R. If we are taking the vector product R cross P, that is L, like that we can take here. We didn't take anywhere the vector, right? So if we are taking the vector, we will get it as R cross V. So R cross P is L by 2m. Rate of area, that is equal to L by 2m. So the law of areas can be understood in terms of conservation of angular momentum also. Delta A by delta T is equal to L by 2m. So these are about Kepler's laws. It's very important, these three laws. Okay, and the diagrams also you should remember. So next we are going to study about the universal law of gravitation. Universal law of gravitation is every objects in the universe will be having an attractive force, a force of attraction or repulsion between them. Okay, so if m1 and m2 are two objects which are at a distance r, then force of attraction between these two objects is directly proportional to the product of their masses and inversely proportional to the square of distance between them. Force acting between two objects is directly proportional to the product of their masses and inversely proportional to the square of distance between them. That is, F is equal to G m1 m2 by r square. What is this G? G is the universal gravitational constant. Okay, G is gravitational constant. Its value is 6.67 into 10 to the power minus 11. What is the unit? Newton meter square per kilogram square. 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. So next, what will be the dimension? How we will find out the dimension of G? So for that, if they are telling you to find out the dimension or unit of G, first you should write down a formula including that unit. That, okay, here G means we can write it as dimension of F r square divided by m1 m2. What is the dimension of F? mlt to the power minus 2. R dimension is L square divided by m square. M will get cancelled. You will get it as m to the power minus 1 L cube t to the power minus 2. This is the dimension of G. Okay, clear? So this is how we will be finding out the this is the scalar representation of force. Now how we can represent the force in a vector form? Okay, so here you understood, right? Force of attraction between the two objects is directly proportional to the product of their masses and inversely proportional to the square of distance between them. F is equal to G m1 m2 by r square. Value of G is important and its unit also important. Newton meter square per kilogram square. So using this value only, using the F is equal to G m1 m2 by r square. To find out the unit and dimension, what you should do? First find out an equation including G. Okay, so next we are going to find out how we can represent this vector force. Force as a vector quantity, as a vector term, how we can represent. Okay. Next is universal law of gravitation, how we can represent it in vector form. So I am considering two masses m1 and m2. So this is the plane. Okay, from the origin, m1 is at a distance r1, and from the origin m2 is at a distance r2. Okay, so displacement vector r will be like this. So this is the representation of displacement vector using r1 plus r equals r2. So r1 minus r2 equals r2 minus r1 will be equal to r. This is the representation of vector. This one how I wrote like this, using triangle law of vector addition. See, continuously, and we know the displacement vector should be from the this r is the displacement vector. Displacement vector I got it like this, r2 minus r1 equals r. Now how I am going to represent f? F is equal to g m1 m2. Here r is the only vector term in this equation. So f is equal to, g is a constant, m1 and m2 are not vector quantities. So it is r square we will write, isn't it? So to convert it into a vector, we will write it as r cube into vector r we will write. Unit vector r. This will be the representation of, so we are multiplying and dividing with one r. So in that way here we will be writing the r cube term. Okay, this is the vector representation of gravitation, universal law of gravitation. And here we know it is vector r we are writing. So this will be giving a vector quantity, right? So here we should give that as a magnitude of r cube. And we know it is in the opposite directions it is acting. It's attractive force, right? So it is negative. Okay, f is equal to minus gm1 m2 by r cube into vector r. This is the vectorial representation of force between the two objects in the universe. Okay, even if two other celestial objects or between the objects, all the objects, this will be the vectorial representation of force acting between two objects. Okay, next is Cavendish experiment to find out the value of G. What is Cavendish experiment? So here I am considering two lead balls, small lead balls, and in between we are considering, see here I am considering two big balls having mass capital M. This is of small m, this also of small m, this is of capital M. So these two are at a distance r, and these is from center it is L. Okay. So we know there will be a force of attraction between these two objects and between these two objects. Okay, so if we are taking a rod which is fixed at one end and which is suspended having length 2L, and if I am taking two large masses having masses capital M to the sides of it, to one mass it is to the right side, to the other mass it is to the left side. Then it will be these two force of attraction with respect to one fixed axis will be causing a torque acting on the system. Okay, if 2 is the torque acting per unit twist. Okay, it is the torque per unit twist. Then if it is twisting an angle of theta, what will be the total torque acting on the system? Total torque acting on the system will be equal to tau theta. Tau is the torque acting per unit twist, and if theta is the angle of twist, then total torque will be tau theta. What will be the force acting between these two objects? F is equal to Gm by L square. Sorry, R square. R is the distance between these two, right? So F is equal to Gm by R square. Because of that force also torque is there, right? So what is the torque acting? F into R. Gm by R square into distance from the axis of rotation L. So this also torque. So we can equate these two. Okay, while we are equating those two, we will get it as Gm L by R square equals tau theta. So from this we can find out the value of capital G by applying the respective values. Okay, this is Cavendish experiment. So it is twisting at a particular angle since both are kept at different sides. One is to the right side and other to the left side. So tau is the torque acting per unit twist, and then total torque acting on the system is tau theta. Because of gravitational force also a torque is acting. These two torques restoring force per unit twist. So that will be equating. While equating these two torques, we will be getting a formula. From that formula, we can find out the value of G. This is Cavendish experiment to find out the value of G. Okay. Then next we studied about the acceleration due to gravity. Okay, acceleration due to gravity, how we can find out? We are considering a mass m, and m is the mass of Earth. Okay, what will be the force between these two? See, if I am considering this distance compared to the radius of the Earth, this is RE and this is at a height on the surface of Earth. If I am considering, what will be the force? F is equal to G M E by R square, or R is RE, radius square. But force we know it is mg. G M E divided by RE square. Small m will get cancelled. You will get it as G equals GME by RE square. This is the acceleration due to gravity of Earth. Okay, this is the simplest form of derivation. G is equal to GME by RE square. So first I am considering acceleration due to gravity on the surface of Earth. So the object which I am taking should be on the surface of Earth. The distance between the object and the Earth mass is RE. So F is equal to GME divided by RE square. This is universal law of gravitation. So F is equal to mg as per Newton's law. So we will get it as G equals GME by RE square. Here derivations are very important. Now next time if it is at a height h, what we will do? Yes, in the same way, and we will take this equation. And instead of RE, we will write it as RE plus H, and will continue the derivation. Okay, so next I am not doing the derivation. I will be writing down the equations and will be explaining to you. Those derivations are very important. Those derivations are given in the respective videos which I did the detailed video. In that it is there. It is there in the playlist also. Okay. So next we did the acceleration due to gravity on the surface of Earth. We already did it as GME divided by RE square. At a height h's, G of h equals G into 1 minus 2h by RE. Okay, that means as height increases, the acceleration due to gravity is decreasing by a factor 2gh by RE. Okay, so it is decreasing. As height increases, acceleration due to gravity decreases. As depth increases also, acceleration due to gravity decreases. By how much of factor? G minus GD by RE. Okay, so this is how we will be writing down the value of G at a height h and depth d. These two derivations are very important at a height h and depth d. Okay, derivation also you should study. Simple calculation only, very easy to study. Okay, next is gravitational potential energy. It is the work done to carry a unit mass from infinity to a particular point. So work done to carry a unit mass from infinity to a distance r to a particular point, that is called as gravitational potential energy minus Gm1 m2 by r. This is gravitational potential energy. Force is Gm1 m2 by r square. Potential energy is minus Gm1 m2 by r. Okay, don't forget about that. Next is escape speed. It is the minimum velocity required for the object to escape from Earth's gravitational pull. Okay, it is the minimum velocity required for the object to escape from Earth's gravitational pull. That is escape velocity. It's while we are deriving the formula, we will get it as V is equal to root 2 GME by RE. But when we are multiplying one RE in numerator and denominator, we know it is GME by RE square it will be, that is small letter g, so we can write it as root 2 G RE also. In that way also we can represent. Next is orbital velocity. V is equal to root of GME divided by RE plus H. That is for a Earth's satellite. Okay, so RE plus H, this is the orbital velocity. So from here only we are deriving the T square is directly proportional to A cube. That is law of periods here we can derive. That is period of oscillation will be equal to 2 pi RE plus H. So velocity equals distance divided by time. So here distance, time will be equal to distance divided by velocity, right? So velocity is root GME divided by RE plus H. RE plus H. So here RE plus H the whole power 1 by 2 and RE plus H that will be equal to RE plus H the whole power 3 by 2 root GME RE plus H the whole power 3 by 2 we will get. So if I am taking the square on both the sides, T square, this will be a square and this will be RE plus H the whole cube. So T square is proportional to RE plus H the whole cube. That was the law of periods. In Kepler's laws of motion, we learned that it is T square is proportional to A cube, like that we learned, isn't it? So here we are proving that using orbital velocity, and all the satellites will be obeying Kepler's law of periods. Okay, so next we are going to study about the potential energy, kinetic energy and the total energy. Next is energy of an orbiting satellite. What will be the energy of an orbiting satellite? Since it is orbiting, it is moving, it has kinetic energy and the potential energy. Kinetic energy we know it is half mv square. What is V here? V is root GME divided by RE plus H. This is V. So V square will be like this we will get. And potential energy we know it is minus GMM by R. This is potential energy. So while we are adding this kinetic energy and potential energy, we will be getting the total energy. Potential energy plus kinetic energy. So here we will get it as, see, GMME divided by 2 into RE plus H minus GMME divided by RE plus H. Here GMME into RE plus H is common, right? So here we will get it as GMME divided by RE plus H into 1 by 2 minus 1. So we will get it as minus GME into M divided by 2 into RE plus H. Total energy is a negative quantity, like that we will be getting energy of an orbiting satellite. Okay, so this is how kinetic energy, very easy to remember, minus GME by ME divided by RE plus H is potential energy. Kinetic energy is half into M into GME divided by RE plus H. And total energy is one negative sign you should put along with this. Minus half into GMME divided by RE plus H. This is the total energy. Next is geostationary satellite and polar satellite. Geostationary satellite. So these are the satellites which is moving parallel to the equator. It will be moving parallel to the parallel orbit of the equator. So if I am considering it is at a distance of 36,000 kilometers from the earth and its period of revolution is 24 hours, same like that of Earth. So from Earth, while we are seeing the object, it will seeing the satellite, it will be stationary because its period of revolution is same, 24 hours. When it is moving, this also will be moving. When Earth is moving, this also will be moving. So both will be looking like a stationary, that is geostationary. So it is 36,000 kilometer away from the Earth. It is 24 hours. Its period of revolution is 24 hours. That means it is parallel to equator, we told, right? So it is equatorial plane and orbital plane. Orbital plane. If the angle between these two, while we are considering, the angle will be 0 degree. Okay, this is mainly used for communication purposes. Okay, this is the use of geostationary satellite. Next is polar satellite. Polar satellite, this is parallel to equator. Okay, polar satellite means it will be parallel to poles satellite. Okay, it is parallel to poles. It is at a height from 500 to 800 kilometers away. Okay, it's very nearby. Polar satellite will be very nearby. It is 500 to 800 kilometers, and it will be along with the equator. Equator and polar satellite. This is equator plane and polar orbit. These two are at an angle 90 degree, and this will be used for remote sensing. Remote sensing to find out the amount of water or forest area. So all those purposes we will be using this polar satellite, and its period of revolution is 100 minutes. Its period of revolution is 100 minutes. Okay, so these are about the polar satellite. Okay, this is very important, geostationary and polar satellite. These two differentiating between these two satellites, you please thoroughly study very thoroughly. Okay, and then next is weightlessness, that you know it is the when we are observing the object, it is showing a weightlessness. The object is freely falling down. So when it is falling down on the way, while we are checking, the object will be in a state of weightlessness. Okay, so that and all in detail I told you already, and this is a quick revision part for this chapter. So I hope it is useful for you, and if you feel it is useful for you and it is interesting to you, and please don't forget to subscribe the channel. Okay, so thank you for watching. Bye.